Okay, I've been kicked out of my apartment. Oh, God, it's really sucks. I can't even make a video. I'm making a video outside. Let's see if it works. There are going to be some birds and maybe dogs in the background. Sorry. And here's what I'm trying to do today. I'm trying to. I've listened to a video, and perhaps I'm even going to find this video and put a little clip on it. And I've talked to other people like Max who said, "Oh, here's what's the future going to be. We're going to take our solar power, store it in batteries, because everybody's talking about storage and in batteries. Then we're going to take the storage and the solar power and use it to make hydrogen, and then we can take that hydrogen and do whatever we want with it." Now, if you think about a picture of a battery, or think about what goes in a battery, and you think about how often you have to store a battery, isn't storing things in a little cask a little bit easier than here's a battery storage and a cask storage? So here's what we're going to do in this video. And my objective is really, I'm going to be a little more technical this time, sorry. My objective is to come up with a way to measure the cost of storage, the solar storage in this versus solar storage, versus making solar and then storing, using the solar to make hydrogen and then storing the hydrogen and getting exactly the same amount out at the end of the day. Okay? Now you can do two things. One is Option one is we can make, that's our electricity option, and I'm going to have to do a little of this as I go along. And option two is to store the hydrogen. Excuse me, I might be able to fast forward some of this crap. I hope I can. Okay, and so if we store the electricity, we're going to make our solar project, our solar whatever, can't call it a plant, a solar farm too big. When it's really big, we're going to use some of the electricity that we produce when the sun is shining to send it to our electrolyzer. Maybe I should have made a picture, but I don't have to make a picture. I'll tell you why in a minute. The rest we'll put in. We'll make the solar project too big, and then we'll use the extra solar to charge a battery. And I've made a bunch of videos. Tetwa, Napakpa. Oh my God. I can't say that. Then I'm going to say that we need a 75% output. And the reason I did that is I met some wonderful people who said, "Oh no, the government of Singapore wants you to put batteries everywhere and to get the solar from different places and store them in batteries, and we have to figure out how much all that costs." Option two is very different, not very different. Instead of oversizing the solar, we're going to oversize the electrolyzer, and we're going to uh, uh, take the solar power we produce and make. I guess we'd have to oversize the solar too. That doesn't really matter. But we're not going to put the solar. Oops, there's somebody driving a big SUV around here. Oh, God. We're going to oversize the electrolyzer, and we're going to put that extra amount that we don't need right now. Basically, we're going to do the same thing, store it in this cask instead of so we'll make it. We'll make it. We'll make a bigger electrolyzer, and then we'll put it all together, and we'll achieve the same 75% output over the course of the year. And this time, instead of financing the solar lithium batteries, we'll do that. Now, I want to show you how to set up a true economic analysis. And I have today I opened these big project finance models, which I make, myself, gigantic models. Oh, and it didn't have to looking for just the cost of a battery and what they really have. That's what I want for these models to do. But they didn't put the levelized cost of the O&M for the solar. I couldn't find the battery cost. I couldn't see if it was there or not. I want to see the real drivers, please. And these wonderful project finance models can also be distortive because there's no refinancing in these models, and there's no reflection of cost of capital changing, and blah, 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 blah. So we're going to use the levelized cost of hydrogen in both cases. Now, just to introduce things, one of the reasons I made this model is I get to show you kind of what we worked on a little bit. And I have these classes, and in this was oh, I got a Herr Dr. Barner ist da. Ich muss schließen. Okay, I'm going to close this one. Okay, and here we're going to take this spreadsheet. Now, this is horrible. This is the Lcoe Summary. Okay, and I'm going to say, okay, what we want to do is, in this case, we wanted to compare three strategies. Strategy one was to make a solar and battery. Strategy two was to just use a natural gas combined cycle. Strategy three was to use a solar plus combined cycle. Now that's really bad because natural gas produces bad, and not only carbon but methane. I totally agree it's bad, but I just wanted to show you how to do that. And they all produce 75% capacity factor. And we want to reflect the details of the solar in here. Are we tracking solar, or are we just using a fixed system that's tilted? Here's our so I put a temperature coefficient, not very high. I put some other performance ratios in here, so I want to show you how we can walk through all of this. And then I said, oh, here's our load. We just want to hit 100, and we want to get that 75% of the year. And so you just take that, multiply the 75 times 100 times 8760, you get the total amount of kilowatt hours we want for the year. Okay, and then we can do it quarterly. And how much solar capacity? Well, we're going to oversize the solar to get there, because the solar itself, we'll see just a minute what the capacity factor is. So that's going to be we're going to produce this much electricity, and then we'll get it into hydrogen. Now, the way we'll get it into hydrogen, just a minute, we'll put the we'll find a good electrolyzer example, and this electrolyzer example might have something like a efficiency that, let's use this one, not this crazy one in the future, this 52.08. Now, if you open the generic macros, which I'm going to go through again, I'm going to put just 52.08, and that's our kilowatt hours to kilograms. So if we have this many kilowatt hours, well, we have to reverse this, 1 divided by 52, or we can put total hydrogen produced. Now, the reason I can get some words out. I really can. The reason I'm doing this is like this. The reason I didn't do it before, we want to produce that same amount of hydrogen, and we don't want to produce it from the batteries with our 75% target load factor, but we want to produce it from the hydrogen storage. Now, maybe you've turned this video off already. Fine. Because this is going to get a little more technical than the other ones. The answer, I'm gonna have to go back and change this dramatically. The answer is pretty obvious. The answer, if you just look at what it takes to make a battery, a lithium battery, how expensive it is versus a silly little, not a silly, a beautiful cask that's got some good metal around it, and you can compress the hydrogen in it, so it's not that simple. It's not quite like a box or something. But I would submit to you that it's pretty intuitive that it's going to be one heck of a lot cheaper to store the hydrogen in a cask and make and oversize our electrolyzer in order to store it rather than storing the electricity in a lithium battery. So that's what we're going to go through and work on. Okay. Now to get there, okay, first, what we're going to, you don't know, okay? If you here, I don't know what I should do. Maybe I should put a little thing here. We're going to get our economic analysis correct. And I'm going to press Shift Control 7. I've got no generic macro open. And then, whoops, this is maybe this is our total strategy 1 of battery and solar. This is our strategy 2 of natural gas combined cycle only. Don't cry about this. Don't cry about this. I suppose I'll select that one too, okay? And Shift Control 7. And this is our strategy 3 of let's put it over here, NGCC plus solar. Okay, and when we go through this, now we're going to use the same sort of analysis. Okay, we're going to use the same sort of analysis, and I frankly don't know what exactly the policy implications of all this may be, because and I didn't put right now I didn't put any variable cost. I didn't put any down here in the variable cost section. I didn't put any emissions cost for our natural gas. So if you put a really kind of high cost there, it might change things. But and we're going to go through the hour by hour dispatch in the solar. So in this case, we have oh, excuse me, the little dog's down there. Okay, whew, making a video. Okay, and if we just put solar alone, our LCOE is, oh, I can't believe I didn't do this. I didn't center this. Okay, our LCOE, if we just do the solar alone, because we put this extra capacity into the solar, and then we used a 700, and that was my number that I was told to use. Okay, for solar, and then we get our total capital cost. Maybe I should put a little Shift Control E. And the reason I pressed Shift Control E and that worked is because I have the generic macros open, and I'm going to go through a little of this generic macros that nobody uses ever, and it's getting better. I promise I'm working on it. I've not got it to the stage where I can do an audit. Now, when we put our capital in, we have to put the lifetime of our project. I understand, we'll look at this in a minute, that a battery can have different lifetimes. And if you start wasting your time and you're doing an economic analysis with some big model, and then I guess we could replace the battery 3 times. And if you really wanted to put a learning cost in, you could. Okay, but I'm just talking about the solar. We put all the tax parameters in. We put all of the debt cost and the equity required return, and then we get a recovery factor, which is it's that I did this in total USD, but this should have been USD upfront, and then this should have been USD per year. Okay, and then we can I put all the O&M costs in. In this case, I had an O&M cost. When you're doing a analysis, LCOE analysis, you can't just say, oh, this is only O&M. It's really O&M plus all the accounting cost, insurance cost, any property tax cost you have, anything else. Let's press Shift Control C. Let's put a decimal here, okay? And then you can put this is in USD per year. So we're putting this cost, and all I'm doing is taking the 15, multiplying it by 300 of capacity, and we get our total USD per year, and then our total cost in again USD per year is this, and then we put our total production in USD per year, not in USD, in KWH per year. Ooh. And then we divide them, and we're careful to use real costs. I've shouted about that so much. USD per kilowatt hour. And we get 1.9 cents in this kind of scenario with these kind of parameters. And then it's not so hard. We put in the battery cost, but we split it up. This time I've learned that you should split it up. We don't put a degradation. Instead, we say part of the cost is for the just a minute. This is up here. Part of the cost is for the battery banks, and part of it's other. So if this is 70%, I'll use that. The batteries have to be replaced in 10 years, but the rest of the equipment can last in 30 years. I'm going to use that. Now the total cost of our battery here, if I look down here, is 300. That's the cost I was given. I was told that the blah 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 blah. Where's the operating life? Come on, here that the operating life of the battery, I've used 10. They wanted me to use 13, and each time I change a parameter like that, I get a different total cost. Now you have to be careful if you're saying, oh, this 1.9 becomes 8.9 or almost 9 cents per kilowatt hour, and it's all influenced by these kind of parameters. Of course, I'm going to give you the sheet, and you can put everything in, but we really have to know how much battery capacity in kWh do we need. And the kWh of battery capacity here was 300 kW, but we needed a duration of 3 times 5 is 15. We needed a 15 kWh, so that's what we put in to get our total cost of the battery. And that's what it gives. Now, if you would have said, no, that's 75%, that's absurd. Let's make it 50%. Okay, and then what happens is you overproduce. So this time we could put a smaller battery in if we want. And you can see now we're getting close to the target, and we can put in a smaller, a lower, a lower duration. And when we do that, assuming we don't need nearly as much battery capacity to make our extra load, then the battery capacity, the storage is a whole lot more interesting, and well, more interesting, it's a lot more economic. You see, there was the cost. And let me show you how we got there. Okay, and this one, if you, my suggestion for you, okay, now we need to get our 75% here to be able to produce 75%. I'm going to show you how we work through this on an hour by hour basis, okay, and let you work through it. I'm not going to take you through every stupid equation, okay? But I just want to give you an overview and to have you not be intimidated. Now, I picked a place in this wonderful Malaysia because I'm going there. And in Malaysia, I use this PVGIS, and they said, oh, okay, let's get to the bottom of this. If we use a tracking system, we get 22 something 8. That's per year. Okay, and then don't look at this yet. And then what we do is we go through every single and you go to that website, PVGIS EU, fantastic, unbelievably cool website. Sometimes they get some of the data wrong. You can tell because if when you graph the hour by hour, it gets crazy a little bit. But here's the oh no, I'm going to do something here, and here's the output. You can see these numbers are obviously wrong. Okay, and that wasn't so bad. And if you use your generic macros that you just go and download, and I'm working like crazy on this one, and I'm going to put the top here. I'm going to make this black. I don't know what it'll be. So the yellow numbers, and I put these little things in so you can see how long it's taking, and it doesn't mess up your computer, and it doesn't blow up anything, and you don't have to go and buy some silly little program, and now it's taking a little bit longer, and now it's going to the next stage, the linking the color, which takes the longest. And it's taking one whole heck of a lot longer because I'm making this video. And now it's finally over, and it's done all the coloring for you. And let me go back. So these, when it's green, you're taking it from another sheet, and we're putting the quarter by quarter in, and then we put the amount of production here, and let's sum this. Now it might not sum exactly to that number we had. I'm going to press Shift Control D. Oops, no, I'm not. Shift Control C. I got to do this. Shift Control. I put a new one in, and I forgot what it is now for the videos. Let's divide it by 1,000 to get it into. Ooh, this is how much power we get. So this is not exactly this, but when I did this over many, many years, it gave you 2288. So that's not that far, is it? Okay, so then you put this in, and then they give you the temperature. Now this temperature is kind of BS because it's not the temperature that's hitting the panel, but so what? And then I said, okay, let's adjust this. So I said, okay, let's take out anything that's greater than 1,200. Let's reset it to 1,000. I could have said 1,100. Clearly, there was some funny little data in here. And then I said, let's assume a temperature coefficient. And the way a temperature coefficient, when it's less than 25 degrees, you get a higher amount. But when it's higher than 25 degrees over here, you get a lower amount. It's just a linear equation. You can see all I did here was took the percent change versus 75, and then we take that percent change, and we just reduce the output by the temperature coefficient times that, and then we get the watt hour, and then we put in the net production we actually get. And I said, okay, let's put a different kind of performance ratio in here. So we can put 12% losses or more, and that includes losses because of the sizing of the inverter and everything else. And then here's our target load, and here's our solar production. So our solar production is, we net everything out. We've got to multiply it by our 300 divided by 1,000, the SEC, and we get our solar production each and every day. Okay, and then we say, well, okay, in some hours, then we start working through a battery dispatch, and we say, okay, in some hours, we've got more, we have this surplus solar. And I used to do this day by day, and I've come to the conclusion it's so much better to do it hour by hour because you can just keep opening balance, closing balance, opening balance, closing balance. That's all you have to do. That's what's left over to store the battery. And then you better put the storage capacity in kilowatt hours because if you run over the storage capacity, you're not going to be able to use the battery anymore. And you're going to do that with a minimum and maximum. So the remaining storage capacity, you kind of put that in, but now this A something 13 should be over the opening balance of the storage capacity. So you see, let's go down a couple and you see how much is left over to store. This is our maximum amount of capacity. This is the amount we have in the battery, just like you have in debt an opening balance. Oh, this opening balance helped a lot. And then you can say, well, what's our maximum amount we can store just in one single hour? And I thought, well, that should be kind of like the solar. You want to be able to store all the solar power you have. You don't want to waste it. You could try a different strategy. I think there are loud things going in the background, and I'm just shouting a bit. And then you can see, well, here's how much we're charging the battery. We're going to use some of our solar for our own purposes, and then we can put our round trip loss in there as just how much we charge minus the round trip efficiency, and we can get our discharge, and you can go and get this file. I'm making this video. If I put this file up there on the website, nobody'd ever look at it in 1,000 years. Like they don't look at my these things I work on so hard. Oh, and then we can see well what's the limit we have on the then excuse me, we have the depth of discharge. Now the reason those batteries can last longer is they will absolutely make sure you never go down below the depth of discharge, which is good news for the length of the batteries, bad news for the economics because we got to put a bigger battery in to meet our target. And then we put our opening balance in. So we put the limit on the maximum amount we can discharge here. We can't take more than even if we want to, we can't take more because we got to leave this 195 down in the battery. Okay. And then we go through and we finally say, have we wasted any solar? And this is the amount. And we see if this is going to kind of over the course of a whole year. Now, I first did this for 15 years because you get 15 years of hourly data and the file went way too big. And here, oh, we got some, we don't, I'm hoping we get more hours here where we don't have enough. And maybe I need to go to the rainy season to kind of see that. And then what's so important in this kind of stuff is that you you're able to graph it. Okay, so let's say we go to March and we can see what happens in March. Let's say we go to September and we can see that we have different solar. We can do it over a week, a month, a day. And this battery balance shows you the depth of discharge, how much extra you have, how much you're taking out. And we can try for a different date, a different day. And this whole thing works with match, index, match, index. The whole thing works is all you do is you put a date and you match that against what's in that big file that you get. And then you hopefully somewhere this better be index. Oh, I put the index over here. Then you put the whole 730 for a month. You put what the start of the match is, and then you just use the index with the match index. I could have used, I think, XLOOKUP. Sorry, I should have. Get used to it, and then you can see what happens to the battery balance. Let's put 12. What happens in month 12? Whoops, that's a little bit too because we ran out of the end of the year. And what happens? Whoops! Oh no! I didn't mean to do that. I hope it doesn't completely break. Okay, so in this case we're not being able to discharge much. We have some problems with the solar, and you can really illustrate here. This is the solar we use for the output, and then we don't even produce enough solar here because it was cloudy, and this is the extra solar that we're using to charge the battery, and this is how we're discharging the battery, and we had nothing to discharge here, and that's how you get to that 75%. Okay? That's working through hopefully a little bit better battery storage and discharge. Shh! Tais-toi! Okay. And then now what we're going to do is put, oh no, shh, 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 tais-toi, kayate. Okay, now what we're going to do is let's take this electricity we made. Shh, I gotta pause the video. This stupid thing. Shh. Now, so here's what we're going to do now. We're going to take and combine this with a with a with a hydrogen analysis. Excuse me for not getting some words out. And let me just basically set it out. So what we're going to do is here we'll put electrolyze we'll put an electrolyzer using a battery and solar. That's what we're going to put over here, and then we're going to have to put on our capital costs, and somewhere we'll put on our production first. And we have to make absolutely sure that the amount of production we have in kgy is the same in this case as it is in another case where we have an electrolyzer, excuse me, where we have an electrolyzer instead of using the battery and storage, we have the electrolyzer using the hydrogen H2 storage and solar. Okay, and in this case, we'll put in our electrolyzer cost, and as we always do, sorry about this, we'll separate the stack from the other. Okay, and when we do that, we'll eventually get our total cost. And then this time we'll put our total capital, and eventually we'll have our total operating. And then in our total operation cost, of course, we'll put our efficiency in terms of kWh divided by kg. That's our 50 or whatever. And then we'll put our cost of our electricity, and that will be USD, KUSD, whatever, per kWh. And then we'll have our total energy. Okay, and then somewhere down here, and maybe what we really need to do is put a couple of extra things up here and, upstairs. And I told you I was going to do this, and I didn't. And maybe we want to put this in column B. And okay, and our total capital cost will be our electrolyzer. And that might be in, I don't know why they do it in kW, but whatever, because it just confuses things. Somebody commented on it, and that's right. And up here, what we'll need is also, we'll need our capacity. And our capacity will be pretty simple. If we're having it might not be. We'll look at hour by hour, and we'll basically, we had that target of 100 kilowatts in an hour, so we can take that 100 kilowatts. I guess we'll divide it by the 50 to get the 50.2, 52, whatever it is, to get the total. So that will be in kg. We could put it in kgh or just kg. Maybe we should just put it in kg. Okay, and then we can get our capital cost. And once we have this, and then we'll put other O&M. And I'm just, you know, we can put this as a percent and then a total other, and that would be USD per year. And finally, and so after we put the USD per kW, the efficiency, I'll put that back. And we'll put that in kWh per kW, and then we'll get our total capital cost. And somewhere down here, we'll get our capital recovery. And then that's where we put all of our things like the degradation, the tax rate, the interest rates, and all that stuff in. Okay, and finally, then we'll get our total cost and LCOH. Okay, that's the way to set it up. Perhaps this is really the most important, and I hope that the reason I'm making this video is I hope that you can get an idea, and then you can take a look at the video, the files. And now, instead of this, we need to also, in this case, consider the storage cost. Okay, and so what we'll, I guess I'll fix the outputs later, and let's put this capacity over here. And so what let's work through this. We need to figure out how much storage we want. Okay, this won't be in the first one. We'll put storage requirement. And this is kind of like we have in our kWh in electricity. That's why I went through that, and that's going to be in kg too. But we don't multiply it over the year or anything, because we store it, we charge it, discharge it, charge it, discharge it, and then we need to put how many hours of storage maybe, and maybe I'll put that. That's the hours of hydrogen storage, and then we somewhere down here we add in our hydrogen storage, and then which is in kg times hours. We have to we can't just take 1 kg. We have to have enough boxes in our warehouse to store the whole thing, and then we can put our storage cost per kg, and then and this is USD per kg, and we can put our total storage cost. And I forgot. And then what we need to do is eventually get down to the capital recovery here. We'll put the capital recovery items, and one of them will be the operating life. And then eventually, or Shift Control Plus, we'll go down here, and eventually we'll get the total capital recovery in USD per year. So we change the USD per year, and then we'll get the total capital cost, which is the capital recovery cost, and then we have the total operating cost, and then we'll have the total cost, and this is all, and my battery's running out, USD per year, and this is USD per year, and then we put the hydrogen production, and we can put that in KGY, and then we can get the levelized cost. And we can now finally really compare the storage cost, the storage cost with a battery and the storage cost with a with a lithium battery versus the storage cost with a cask. And we're going to produce the same amount of hydrogen. And I'm going to now pause the video. I'm going to charge the computer. And hopefully this whole thing worked. And then I'm going to, and then we'll show you how to attach this to this thing called the oh, come on, please. We'll attach this thing to the I call it the LCOE calculator that just works through. It's basically a PMT function that uses the real discount rate that accounts for the taxes, and that accounts for production and degradation and everything else. So I'm gonna pause this, and we'll see you in a minute. Okay, so here's what I've done. I've put the come on, please. I can't go from page to page. I've put the electrolyzer inputs from our other page, where we get the amount of capacity, we get different estimates of the cost, we get the lifetime, we get how much is related to the stack and how much is related to the non-stack. And now when I copied it, Alt-EM, there are some of these numbers, I'm sure somewhere, that they've got this this whatever link in it. So we could press Alt-EK and break the link. Let's do that one. Okay, we could have also, if you would have wanted, we could have pressed Control-Alt-C, and we could have pressed this thing and find and mark external links, and it would have shown us where we have those, but I didn't do that. Okay, and let's here's what I'm going to do. I'm going to move this over here a little bit, and then let's pick one of them. And the one I'm going to pick is this one over here, which is the kind of applied case current. So this is, so we over here, and let me press Alt WFF, and then we'll go over here and we'll take that applied case so we won't lose it over and over and over and over and over again. Okay, so this is the stack portion and the non-stack portion, and I kind of maybe I'll do it here. Why not? Alt WFF, please don't go. Okay, so we can do that. Let's put the I can't get rid of all this shit. That was stupid. Let's just press Shift Alt right arrow and just not show that. That's a lot better way to do it, isn't it? Okay, so we've got our costs, and I don't think I'm going to use a 650 US dollar. Maybe we should use 1,000. Let's be a little more conservative. This is going to be a big issue because we have to figure out how much electrolyzer capacity we need. And if the electrolyzer capacity costs more relative to the fuel, this is all going to be fuel versus electricity. And I have been thinking, and I have somebody else from a class I had a couple of weeks ago said, oh, why don't you always make a little graph where you maybe make a pie graph, a stack bar chart, something where you show how much is capital and how much is operating, because that's the big deal. in electrolyzer, so much is going to be operating. So maybe we'll do that. Now, what we're going to do then is I'm going to go through the hour by hour stuff. And the first thing we'll do is we'll get the efficiency so we can put different levels of efficiency in. And excuse me, oh shit. Okay, let's get our efficiency in right away. So let's get our kWh divided by kW kg. And let's take this 52. Okay, and then shift control C. And by the way, why don't we now, I've got something on here, and this is on column B. So let's put our title column on column B. Let's not use something so dramatic. So let's use this one. And for now, let's not put something right on the top. And then at least you can see how this thing. Oh, be quiet. Shh, shh, shh. Okay, I got it. Oh, come on. Come on, I'm making a video, you dog. Okay. Ugh. I gotta do something about this dog. Now, let's put the Mr. Robert said I could deal with dogs. I don't know how to deal with dogs or women or anything. Okay. Now, we've got we can take the amount we finally produce with the batteries that has kind of our leveled out. We can take this and multiply it by our conversion. Okay, so that's a big deal. And then we can, I'm going to double click that. Now I cheated and put a couple of ones here. Now we can, instead of doing that, get our kilograms from hydrogen by pressing F4 and multiplying it. I'm not going to do any of this solar storage or this depth of discharge or this round trip efficiency. I'm just going to go straight to my solar production here. Okay, and this is here. After we've gone through all of our performance ratio, all of that, we have our net production. And we're just going to produce all of that, and we're going to shift control C, and then I'm going to take that solar production, and this was kilowatt hours. This was, I should write this down. This is kWh divided by kg. So if I want kg, I don't multiply it, I divide it. Excuse me for doing something so stupid. Okay, and I do a lot of that. So that's, we're not producing much. Who cares? We can make this in some other unit. Okay, so this time we're going to just produce it every hour. Maybe we should make this thousands and all of that. Okay, and then maybe, oh shoot. Okay, so let's work through this step by step. So if we go to the hydrogen production, when we're going to produce it at our flat kind of 75% load factor, well, all we do, I think I'm repeating myself a little bit, but we just divide it. I think I multiplied it. And then this is the amount you get directly from solar. Now, if we want the, I'm putting we can make a little bit more from we don't have all those constraints on the battery, so I put a little factor in here. And if we, just a minute. Ooh. I'm going to come back to that one later. I did something horrible by saying, just put a little factor in there. But it's basically we can produce more, and we're going to look at how much we have to store in the battery. Then we take the amount we produce in our flat kind of scenario and multiply it times this little factor. If we have more solar than that, we use a maximum statement to make sure it's not equal to zero and not less than zero. We take the difference. Then we see how much we can produce. We use another maximum statement to make sure it's not negative. And then we put our opening balance and we add to the opening balance the amount we put in our casks. And then we subtract the amount we take out of our casks. Okay, and then we can look finally at how much storage we need to get the same kind of result. I'm pressing F11 and we need something like, what is this, 27, something like that. We can see how much is our maximum storage capacity. That's how many kilograms of storage do we need? How big do our boxes have to be? Now, for the next step, so once we have this, now let's go back and see how big our electrolyzer is in this case, where it's just flat. In this case, we have to be able to have a bigger electrolyzer because we're going to store it ourselves. So we're going to consider that. Of course, we had a bigger solar in this case too in order to store it. So don't think that hydrogen is somehow inherently more expensive because of that. Okay, and then once we have these parameters, we're going to put them into our LCOH analysis. And once we put them into our LCOH analysis, we can, at the end of the time, look for this strategy versus this strategy and get the totals. Now, instead of you watching me connect a whole bunch of things with this where's our detailed LCOE calculator, what we're going to do is I'm going to show you very briefly how to do it, but I'm going to switch off the video for just a minute and okay, so here's what I've done. Let's work through it. I thought it would be too much torture going through the whole Excel stuff. The final result is that by adding hydrogen storage instead of electricity storage, you get about a 55% of the rate, or otherwise saying, let's do it this way. The cost of putting the storage in electricity instead of the hydrogen is about 76% more. Okay, now let's see how we got that. And you can see that it's an objective, I hope it's an objective analysis. And let's see some of the nuances and things that are a little bit interesting, a little bit different, and that you might just have to think about a little bit. The first thing we do is we get our total amount we produce from the electrolyzer. And if we produce it directly from solar without the battery, okay, there's a little bit of a difference in production. That's what I put in. And then we have a lot more capacity, because when we went to the hour by hour analysis, here we flattened everything out, and the only amount of, oh, that's pretty loud in the background. I'm sorry about that. Oh, I hope you can bear with it. That's the maximum amount of capacity, and we flatten it out. If we use it with solar, we've got to produce all that hydrogen from the solar, because we're going to store the hydrogen after we make the solar. So that's the production, and we start our LCOH or LCOE or LCO whatever, or total cost of production, cost of driving. We start with the production. Okay, and then we can say, well, okay, here's the hours we operate. And the reason we need the hours we operate is, remember, the stack life is a function of how many hours you operate, not just a calendar year. You age based on how hard you work. So I don't work very hard, I wouldn't age very fast. But other people were like you, who are watching this video, you might age faster. That's the way the stack part of the electrolyzer works. And to get that, now I'm pressing control and the little square bracket to get it. I just did a count and for the if we flatten the hours out, we get about 7,000 hours. If we're just operating when there's a little tiny bit of solar, even a tiny little bit of solar, I included that. And so I said, okay, we operate a lot more. Now, maybe this would be adjusted and this would be even less. So the lifetime of the stack will be very different than the lifetime of the solar. Now, I said the cost, the upfront cost of the stack, the electrolyzer is 1,000 a kW. I divided that 45% into the stack, 55 to the rest, and I put our efficiency in. Now you can put whatever you want in, and you could even put a lot lower cost, which we'll do kind of at the end. And then we get to the hydrogen storage. And in the hydrogen storage, again, I need to finish this. I really need to finish this, where you can press Control square bracket and find lookup and index and sum if, because those are the three things. And that was a little bit of a digression. And all I did was take the maximum of this storage, and maybe this wasn't the best strategy, you know. I'm pressing F11 again, but you can see that we store it and not store it depending on the solar power. So we get so our electrolyzer doesn't run all smoothly like it did with the flat solar. Okay. Then once we have that maximum, then this is the big deal. Okay, you put 1,000 in for those 32 kilograms, and multiply it by 1,000 million, a billion, whatever. Okay, and that's we got the cost, and then you can say, oh, look at this cost compared to this cost. This storage cost, it wasn't like electricity. In the case of electricity, the storage cost here compared to the solar cost, the storage cost was a lot more than the solar cost. In this case, the storage isn't that much. And you can say, oh, where did you get that 1,000? I looked all over for it. I tried a couple of different sources. I looked in the IEA. Okay, maybe if that's all wrong, well, then put a different number in. And actually press Control Alt C, press it hard, and then let's put some crap on the top in those first five things, and I'm gonna be irritating, and I'm gonna keep doing this kind of stuff a lot on these videos, because I noticed that some people have called me and they say they watch my videos, which is a lot of BS, because they don't, because they have no idea what this generic macros is even doing. So that's an input, okay, and these green numbers come from a different sheet. And then we took, okay, so then we have to take this number and spread it out. And here's the big deal. If you look at the economic life of the stack, in the two cases, we get a longer life. And if we get a longer life and use our PMT functions and go crazy, and on this one I really will tell you, you know, look at another video if you want to see how those are all working. And then, so we get our capital cost, which is more, which is a lot more. Okay, shush, dog. Shh. Okay, and then, now, but then, after that, here is the biggest deal of all. We have 52 kilowatt hours per kilogram. We use this many, we want this many kilograms per year, and here's the cost of electricity with the storage, and here's just the cost of the solar. That's the big deal. And then we get 58,000 for the cost of including the storage, and only 13,000 for not including the storage, and that dramatically offsets this difference in cost that includes the capital cost of the storage. And again, I went crazy in the last year or two almost saying, and when I had to, it was painful. It was so painful working with people and saying, yes, if you do your levelized cost carefully, it exactly matches a project finance model. It really, really does. So please, oh, please, this is the biggest thing. I'm crying, and I shouldn't cry, but use something like this. So then use the levelized cost ideas at least. Think about them. And this is USD per year. So then we put all of our operating costs together, our stack, non-stack, total, stack, non-stack. I didn't put operating costs in for the storage. You can yell at me. You could put some little factor in. Okay, let's put 2% in. Whoops, 2%. Okay, and then we can multiply our 2% by the capital cost if you'd like. Okay, it won't make any difference to anything. And finally, we put our levelized costs together. And remember, these are real levelized costs, not nominal. They're today. They go up with inflation. Like everything goes up with inflation except the money I make. That doesn't. Everything else seems to be going up with inflation, and I'm so sad about that. Okay, it sucks. Well, at least I don't make any. And then, so we put the total capital recovery, the total operating cost, and you can see there's this dramatic difference in operating cost, and that's what drives everything. And please understand that. And that's why with these high costs of natural gas, maybe electrolysis really does look close. It is economic now. Not maybe it's close, and you can figure out the break-even price for that, which is another subject which I did before, and that's how it kind of works. Just a couple more mechanical things before I finish. These numbers, this is the total capital cost. Then you put these inputs into the levelized cost analysis, and then you get them back out. So the basic thing you do is you put the capital cost as an input. These capital costs come from our levelized cost spreadsheet, and then you press F5 to go back. So this one, again, control square bracket. I have to fix that. That's one of my things that I'm going to do before I die here. The capital costs, they come from the total, and who cares if you want to put the storage costs or anything else in. And then you put the economic life in, and that all comes from the other spreadsheet. I didn't do all the coloring on this one yet. And we put all the WACC. I made it totally consistent between the cost of capital we used in the electricity analysis and the hydrogen analysis. And if you go silly, oh, my son's taking this MBA class. God, it pisses me off. It's supposed to be a good one. The crap they tell you. So here, and then you get the income tax effects, and you get if you want, you get the degradation effects, and then it gives you the result. And I've proven this over and over and over and over again. These spreadsheets you get where you put this thing in and you get it out and you show that the IRR is the same as the WACC you put in and all of that. So please don't worry about it. Please convince yourself of that so you can do these kind of strategic analysis and demonstrate that if somebody is telling you I should store a solar power with a battery and then put it in an electrolyzer, they're just full of complete crap. It's just a silly thing to do. Probably the best strategy is hopefully to just run your electrolyzer when it's sunny out and just get the pure sunlight and stop worrying about the capital cost. Understand the difference between what's capital intensive and what's not capital intensive. So that's enough of this video for today. Let me stop it.